Yes, just.
But pOH is the concentration of the inner oxide, right?
Yes, it's a scale to help us kind of relate the concentration. So it's just that taking the concentration and using a logarithm to turn it into a little bit easier number to talk about. That's the whole point of the pH and the pOH scales. Okay, today we're going to talk about the strength of acids and bases. Okay, now strength is not concentration. They're two completely different things. Concentration is basically how much per volume of the acid there is, and we measure it in generally molarity, which is what we're going to use all the time for acids and bases, although it could be measured in grams per milliliter or something like that as well. Okay, so concentration is, basically how much of the actual acidic compounds there are for every unit of volume. And we, again, measure that in moles per liter in most cases. Strength is different. Strength talks about how many, I guess, let's back that up and actually say the percentage of acid or base ions that actually dissociate. Basically all. Well, I guess. Okay, some acids do not completely ionize. And if there's compounds that aren't ionized, well, they're not really adding to the acidity of the environment because there's no H plus ions that are coming up. Same thing with bases. If it's not able to ionize, it's not going to make OH negative ions, whether it's a Bronsted-Lowry or a Arrhenius base. Now, in your packet, you should have a table somewhere on the page. Back page. Strong acids and strong bases. So anything on this list that's considered a strong acid or a strong base will completely disassociate. Okay, so what's an example of something that would be a strong acid off the list? Okay, hydrochloric acid. When you put HCl in water, the water molecules will completely tear them apart. All of the HCl molecules will end up as hydrogen ions and chlorine ions. Of course, we need to remember that this is just shorthand. Really, they're ending up as hydronium ions. But the point is, we can draw a singular arrow here going this way. All of these things end up like this. There's no HCl left together. Completely breaks apart. The same is going to be true of all the strong acids on that list. So if you mix some hydrochloric acid into some water, it's actually pretty simple to figure out what the pH is going to be. because we know all of them are going to break down. So, let's say we made a, well, actually, let's come back to that. We need to talk about Ka values first. Well, no, we don't. We'll do this first. Let's say we made a 0.1 molar solution of hydrochloric acid. We want to know what the pH is. Because all the hydrochloric acid breaks down into H plus ions and Cl minus ions, we know that the concentration of H plus ions is going to be 0.1 molar. Because all of them are breaking down. So if we want to find the pH of this solution, all we do is take the negative log of 0.1. So, a 0.1 molar solution of hydrochloric acid is going to have a pH of 1. And you do the same thing with a strong base. An example like potassium hydroxide. If you have a 0.25 molar solution of potassium hydroxide, we would take the negative log of 0.25. That's going to give us the POH, and we can subtract 14 to find the pH. So for strong acids and bases, all you have to do is take the concentration, right? Calculate what the pH is using the negative log. Now, in most cases, you're not going to see a problem like this. What you'll see is something like this. We're going to mix 35 grams of sodium hydroxide into 0.75 liters of water. What will be the pH of the solution? Okay, so let's try this as a practice problem. What would be the first step here? Okay, using the molar mass, then you're going to use that to find the moles and then the molarity. Right? So that's kind of the first step, is figuring out what the molarity of the solution is going to be. That probably wouldn't all actually go in solution. Not a realistic one, but we'll go with it anyways. The pH is going to be really high.
And what you're doing?
Okay, the first thing you want to find is just the molarity. That's, is that what you're saying?
I'm sorry.
So, just like we did the other molarity solutions, that has changed in acid spaces. We want to find how many moles there are in every lead. So, first thing is figure out how many moles of the sodium hydroxide. to figure out how many moles per liter there are.
Maybe like 1.1 or 1.17.
You got this set up right. It's just 2 grams. This is grams per mole. Grams. What's not this be how many moles? Do you have an answer for this? I'll get there. So
Yeah, there's negative 0.04. Well, it's a very bad acid. Yeah, highly concentrated, so pH is a little bit different.
yes, like
14, and then some, it's
negative. It's a little over 14. So I mean, and that's possible. Like I said, you can have a negative pH. You can have a negative pH. You can have a pH that's over 14. It's just typically rare because that would be very concentrated. Like I said, you probably wouldn't get all 35 grams to actually have some.
oh, yeah.
But
You're right.
that right side of the
Oh, no, that'll convert it over to pH.
this many units of the sodium nitrate.
Oh, you know what? I think
Then
we
there's
should.
the concentration.
I don't know.
It seems like those seniors that have the operations just keep going until they're not going to you will change the negative.
Okay, we got this many moles, right? Well, that's times that. Yeah, moles are just many moles.
It'll work. So it's barely. So it's a 4. It's a no. It works. It's just pH and negative 6 kilo. Negative.
Did I do that part?
Yeah.
It's the concentration.
Okay,
Okay, that's the concentration of sodium hydroxide. Because sodium hydroxide, what's on this index,
Exclamation.
you know, every single one of these molecules is going to
Backspace.
So that means the concentration that you have there is going to be a concentration of the weight here. That would be your three options. Divided completely the wrong way. You take the number of grams divided by the number of mass.
4
Divide the moles.
Actually, no. Easily recognizable, but now it looks like something that travel.
pH does that.
But I do kind of like the new color scheme on the inside.
I don't know, it's hard to notice sometimes.
Probably not because it's all about.
Jesus, they already got married? Oh my god. Who's that? It's Cody Johnson and his, well, fiance like 3 weeks ago. Cody Johnson is getting married. Apparently.
He got married.
I know, but I didn't know he proposed like 3 weeks ago. That could be. I think he just married her to go to Paris. Since when?
Well, in pH, this is actually their pH.
But
What do you mean?
where, well, I know where I get my hands on a steak like that, but I'd have to go.
What do you mean to get out?
Because in the Marines, when you live on base, you live on the barracks, unless you're married, then you get a house. Actually, it's with all of the armed forces, but.
Nope. This is the pOH. We have to subtract that from 14, not add it. 14 minus minus negative 0.6.
0.6. Negative 0.06. What? What?
Yep, that's right.
It should go up. That's okay.
Okay, so if you do this, you should get something like 14.06 as your pH, which is, as I've kind of said, not necessarily realistic. I put too much sodium hydroxide in there. I don't think all that would go in solution if we were to actually do it. But the calculations still work out. Should we try one more of these before we move on? Probably. Strong acid list. Okay, let's mix in 1.8 grams of nitric acid into 500 milliliters of water. What would be the pH of that?
That'd be nitrate, right?
That
That'd be nitrate.
It ain't there.
So, first,
That's okay.
Yeah, that's right. You do that. One other thing, 0 to be 8 is 5. Right now we're doing strong acids. At 20.2 strong acids. Actually 6.
That's most probably.
divided by 0.5. I got 12.7.
Yeah, I got 5.
I got 12.7.
pH?
I got 12.7.
I got one.
This is an acid. You're not going to have a pH 12. Where did I were you doing it exactly the same as the last one? Because we did feel it.
Yeah, that was base. Just take your point.
You don't need this right here.
Negative
That's for concentration.
Mr. Roark.
Yeah.
My brother told me you skipped the bottle water class.
Yeah. You guys are going to be selected, sorry.
Wait, we're having a final on this.
Oh, yeah. What? How do you do it?
Is it gonna be like last year? Where if you do worse than your grade, it doesn't affect it? Wow.
Oh, for Christ's sake.
I did. I got like 1 point.
Oh, I had. Okay, I know 1,000. Let's get for the 18.
Considering I just came up with 1.24.
I'm gonna look at that.
Okay, I get 1.24. Yours might be slightly off because of rounding error. But I think everybody's at least on the same page doing it correctly. So, now we need to talk about what happens if you have an acid or a base that does not completely dissociate. Hang on to your butts.
I'd rather not do, or not have to, because that's kind of awkward.
Let's see.
What's your experience in this?
What would be a good example?
Are we talking about aqueous equilibrium now?
Yes? You're going to want something that's not let's look at hydrofluoric acid. That'll be an easy one. Alright, when you put hydrofluoric acid in water, of course it's going to separate, it's going to dissociate into hydrogen ions, which would be hydronium and then the fluorine, but not all of the molecules are actually going to break apart. They have enough of affinity to each other that water can't completely overcome them. And they're going to end up in a dynamic equilibrium. Some of these hydrofluoric acid molecules are going to be taken apart by the water to form these two things. But there's going to be certain ones of these that are going to meet up and reform the hydrofluoric acid. So here we definitely have to draw the double arrows to show that these things are kind of going back and forth, and they'll reach an equilibrium. That means we can't just take the negative log of the concentration of the hydrofluoric acid, because some of those hydrofluoric acids aren't going to be acid. It isn't going to give up those H+ ions and make the solution acidic. So the pH would be actually lower than what you would expect it to be if it was a strong acid that completely disassociates. So to calculate this, we have to use something called the Ka value. Okay? The Ka is a constant that shows us how much of the acid, what portion of the acid is going to disassociate. So it's sometimes called the acid equilibrium, or the dissociation constant, or just Ka value. So I can write those here. Okay, and the way we calculate the Ka value is we take the concentration of the H+ ions that actually form. We multiply that by the concentration of the F- that are in solution. And we divide it by the concentration of the hydrofluoric acid that are left that are not dissociated. But it's not a strong acid or a strong base. It's almost anything that's going to be on your sheet on the other side, where you have these different values for their associations.
So anything that does not make that list, or makes that list?
Anything that's on this list, anything that is not on this list. You won't find any of the strong acids or bases on this list. That's the whole point. Right? So strong acids and bases, let's do the simple way. Anything that's on this list, you can just take the negative log of the concentration. I'll give you the pH.
On the bread tip again, the Ka.
What are we looking for here? Yeah.
Well, this is how we calculate it. So let's say we found a brand new acid, and we want to know what its Ka value was. We would have to measure the concentration of the H plus ions, measure the concentration of these, measure the concentration of these, and then we would use that to calculate.
So what is the
It's basically a constant that just, it kind of comes down to a ratio, a percentage of these ones that are broken apart divided by these that haven't, the ones that are left. Now the way we're going to use it is we're going to use given Ka values to find the pH of a solution. And we're going to do that using what's called an ice table. The best way to show you is just to do a problem. So we'll do this simple so we don't have to find molarities. We'll ask what is the pH of a 0.0, actually let's go 0.3 molar solution of HF. This would be a part that you really want to pay attention to.
So are we trying to find weight or what?
No, you have Ka and then.
Try to find the pH.
Right.
Just
Oh, so you so okay. Well,
Just stick with me, okay? So, we use what's called an ice table. You write ice down the side. That's why it's called that. But each of these letters stands for something different. I stands for initial. C stands for change. And E stands for equilibrium. Okay, and then across the top here, we need to put each of the things that are going to form from the dissociation. Well, each of the things that are going to be in solution when this gets put in and starts disassociating. So the first thing we put is the initial HF. This would be, we want concentrations here. Then we have the concentration of the H plus ions that will form, and the concentration of the F minus ions that will form. So basically, across the top, you're just putting, this is the thing that we're putting into solution. These are the two ions that are going to be formed from the dissociation. Okay? Now, the first part you fill out is the initial. We know the initial. When we first put this HF into solution, this hydrofluoric acid, into the water, before the water is able to break any of it apart, all of this 0.3 molar solution would be HF. So the initial is basically always what you start with, 0.3 molar. Initially, before any of this stuff breaks apart, there is no H plus ions or F minus ions. So the initial there is going to be 0 in each case. Okay? Now, as far as the change goes, we know these numbers have to increase because some of these are being formed from the dissociation. We know this number has to decrease. The problem is we don't know by how much. So, in true algebra fashion, we're just going to put an X in there. We know we're going to gain a certain amount of H plus ions. We call that X. For every H plus ion that we gain, we're also going to gain an F minus ion. Those two numbers have to be the same. Because if an H comes off, you're left with an F minus. So this is also going to be X. Those two numbers will always be the same. Okay, over here we got to rank up that algebra a little bit. We started with 0.3 molar. For every H plus ion that we make, that has to come from this concentration. So the change here is going to be 0.3 minus X. We're subtracting the amount that's of the H plus that's made from the initial HF.
So do you use both the H and the F X's combined?
Oops, sorry, I got a little ahead of myself. This should be just minus X. 0.3 minus X. Because the equilibrium is where we just go, okay, we started with 0.3, we're subtracting a certain amount. That would be the 0.3 minus X. 0 plus X is just X. And 0 plus X here is just X. These are the values that we're after. Now, once you do a few of these, you'll go, okay, that ice table seems like a whole lot of wasted time. Some of you will start to just see the pattern. The reason why I'm showing you the ice table is because in other types of equilibrium problems that aren't acids and bases, the ice table is very useful. I thought I would introduce it to you because it can be used to kind of organize things here as well.
So if you have like H, or 2H or something like that, and then with the 2, or...
No, we would do those each of those H's separately because they have different okay. Now, the ice table would be much more useful in cases where you have a chemical reaction that's happening and you want to figure out how much of each of the things is going to be left. So you would, and basically you would apply this with stoichiometry. We won't get that far. Now, what we want to use this for is in our equation. Ka equals the concentration of the H plus ions multiplied by the concentration of the other ion divided by the concentration of the starting thing. But at this point, we can fill in for each of those. Okay, the concentration of H plus ions is going to be X. The concentration of F minus ions, well, that's also X. And the concentration of HF is going to be this, 0.3 minus X. And that is all equal to the Ka value. The Ka value we look up from our sheet. What is the Ka value for hydrochloric acid?
It is 6.8 10 to the negative 4.
Correct. 6.8 times 10 to the negative 4. So now we have an algebraic equation. It's a little messy. We need to reorganize it. But this is something we can solve. The first thing that we're going to do is get this crap out of the denominator. And we do that by, since we're dividing, multiplying by the same thing on each side. So these will cancel out. Here we get to distribute. So, look at this sketch calculator. What's 0.3 times 6.8 times 10 to the negative 4th?
Uh, 2.04 e to the negative 4.
So we've distributed that, and then we're going to distribute the negative x times this. So we get negative 6.8 e to the negative 4th x. And that all equals x squared. Okay? Everybody with me up to this point? Okay, all I've done is multiplied to get rid of that thing out of the denominator. Then we have to distribute, since we're multiplying by a thing minus x. Okay, and then here, this looks like a polynomial. We can solve that using the quadratic equation. Of course, we've got to rearrange it a little bit so that it's equal to 0.
Add 6.
So
8 e to the negative 4.
All right, we're going to add this to the other side. x, and we'll subtract this to the other side. 2.04 e to the negative fourth. That all equals 0. This is why I wanted you to bring your graphing calculators. We can solve this using negative b plus or minus the square root of blah, blah, blah. But you have solvers on your calculators. And I hopefully you guys know how to use those. If you don't, if you forgot, talk to each other, because I don't know how to use these damn Casios.
I forget which that's under. It's
Wait, what are we thinking?
This is a quadratic equation, right? So we can use, or polynomial, we can use the quadratic equation to solve this. You can use your solver. We should be able to find 2 roots from this number.
Negative 4 minus 2.0. Where's our square root? You have to use the x beta and then the t, or the x theta and the t.
Okay.
Found it.
When you put this in,
Draw.
don't forget that this one needs to be negative 2.04 e to the negative fourth.
That's a c, right? And then it is g, so root. There's no root found.
There's no root found, you must have done something wrong.
It's a graphing. I'm sure.
I don't know. Yeah. Well, you got the right number, you just got the best. No, you didn't. Didn't you? No, go back. You gotta play it.
So how do you do that on these things?
Well,
Oh, yeah.
I got no root found because it doesn't actually touch the x-axis. You go into the equation has to. Go.
So if someone could have you
What is A?
A is 1.
I got 6.8 e to the negative 8.
I don't know how to do a million.
I got it. You guys know how to do some of these?
2 or 3.
Yeah. Degree 2 or 3. 2.
There's always been somebody in class that knows how to do this.
I got negative .015 and .014. Yes. That number.
Yeah, that should be right, Riley.
Who the hell is that? That is under equation. How many?
There.
Here. Whatever you do, I don't know.
Wait, come here,
But if you use the graph one, it's, you gotta find it.
Look at my level. Okay, wait. What is your A?
It would be 1 is your A, 6.8, root 4 is negative 4.
Because it's,
You don't have anything to
yeah, you use the coefficients. The coefficient in front of this is just 1.
Oh, I don't know why I would.
We will practice this for about 3 days. So, we'll confuse square root. Maybe I need to have Manning show me how to.
I got it. Interesting. Because you just put it in as 1.
That's not the way they're doing it. Okay.
I figured it out, Mr. Roark.
Okay, Isaac has figured it out. Maybe you can show everybody tomorrow. We're almost out of time.
Actually, Riley.
Okay, here's the thing. And using the solver thing might be something we have to go over tomorrow. But once you do, you will always get 2 roots, right? Riley, sit down so I can see you. Okay, let me tell you this last thing here. You always get 2 roots, but one of them is negative. It doesn't make any sense to have a negative concentration. So we always just throw out the negative root. That one doesn't matter. This is the one that we're after. This is the concentration, because X, remember we put up here, X is the concentration of H plus ions. Yes, it is equal to this too, but that's not what we're after. We want to find the pH. So the concentration of H plus ions is the root that we get out, 0.0139. We can take the negative log of that, and that's our pH. So our pH here would be 1.86. And like I said, we will do a whole bunch of these. Hopefully we'll get down to it. I just wanted to go through and show you the way to do them. Okay, for your homework for tomorrow, do 1, 2, and 3. Those are strong acids and bases. You don't need ice tables. You should be able to get those done pretty easy. 1, 2, and 3 on, worksheet 14.5. So do those 3 problems. You got CRT today. If you need help, come see me.